Hey folks, welcome back to my channel. This is the part 3 of linear regression series. In this video, we're going to learn how to code linear regression from scratch. We're going to be talking about how we could program the gradient descent without using any libraries. And of course, we'll be using NumPy for all kinds of matrix operations that we're going to perform. But let's discuss first how we could structure our code. So to recap, this is going to be our univariate data set where we have only single feature here, x, and the labels y. And we see some trend in this data, and we want to fit a straight line, a linear model to this data. And that's going to look something like this. So as we discussed earlier, we would represent this linear model using a mathematical equation that is y equals mx plus c. And you already know that this is an equation of a straight line. Yes, that is correct. Now, what is this y? This y is nothing but our hypothesis function, which is parameterized by x. And I would write this in the form of theta 0 of plus theta 1 of x. So this is nothing but mx plus c. Now, our end goal is to optimize these two parameters. These are the parameters that we need to optimize to fit this straight line into our data. So the best way to do this is not to program this explicitly, but in a different way. How we could represent this exact calculation is through a matrix. So I would say a 1 with an x, and take a dot product with theta 0 and theta 1. So I'm representing this part of the equation as a matrix calculation, and that would give us y. So the size of this matrix is 1 cross 2, and this is 2 cross 1, and this would be 1 cross 1, a single result. This is an example for a single data point or a single training example. For let's say we have 100 training examples. In such a case, we would have a bigger matrix, and we have x1, x2, and that until x100. And we have ones, and as always we have these two parameters, and the resulting values will be this y1, y2 until y100. So these are the predicted values. This matrix represent the predicted values. So if we implement our code using NumPy to take a dot product of these two matrices to arrive at predicted values is easy. The reason why we have stacked 1 here is because the coefficient of theta 0 is 1. Now there are two main functions that we want to carry out for performing linear regression. So the first thing is computation of cost. So compute cost. And the second one is to perform gradient descent. Perform gradient descent. Now let's write down the cost function. As you know, cost function is parameterized by theta 0 and theta 1. Now our aim is to minimize this, and as we know here, this part is our loss function, and this is our predicted value, and y is our actual value, or the labels. We will implement a function that would make this calculation for us. The second part is the gradient descent. Now let's write an algorithm for that as well. Now we want to run several iterations to nudge theta 1 and theta 0 so that our predicted value will be closer to the actual value, and that means the error would reduce. Again, we can implement this using matrix multiplication, and it looks something like this. Now let's define our terms here. M is the size of the training set, or the size of the data set that we have, and alpha is the learning rate. I represents the index of the training example, and theta is our main parameters to be optimized. These are the coefficients of x, that is our training set, and y would be our actual values, actual outcome of ith input set or ith training example. Now h of x is our hypothesis function that is parameterized by theta, which is a function of x. Now that we have discussed what are the things that we need to implement, let's get right into coding. Now, I have downloaded a sample data set from the internet, and these are the x and y values for our code. So for a given x, what is the actual value y? And we have two columns. This is a univariate linear regression, and we have this many rows of data. Now let's open up a Jupyter notebook and let's import some libraries. Import numpy, mp, import os, and import matplotlib. All right. Now we're going to use this OS module to open our data set and import that into our numpy object. So data equals load text. So since that is our text document, os.path.join it. The sample data is sitting under the data folder. So let's go inside it and sample dataset .txt. Now the delimiter is comma. So we have a comma between the values. So I'm going to give comma as the delimiter. So let's collect these into our variables x and y. So the entire data, we want all of the rows, but only first column indexed by 0. Now for y, we want all the rows, but the second column. Now let's see. We've got x and we've got y. What's the shape of this x? We've got 97 rows. So 97 is the size of our data set. As you can see here, we've got 97 rows. And the same apply for y as well. So we've got y and x extracted into our variables. So the next thing what we want to do is we want to plot this and visualize our data set. So let's write a function to plot our data. So plot data that takes in x coordinates and y, and let's say we want to plot a figure. plt.plot, and let's pass in our x and y values and mark it with red circles. Alright, now we'll also want to label our axis. So x label x data points, and we want to do the same thing for y as well, which is the label. Now let's plot the data. So this is how our data looks like, and we want to fit a linear model in this data. Let's go ahead and find out what is the size of the data and extract that into a variable. M is nothing but the size of our data. So this would be y dot size. This is what our M is, 97. That is correct. The next thing what we want to do is compute the cost. The first part is to compute the cost, and the second is to perform gradient descent. Let's write a function to compute cost. I would name that as a compute cost that takes in x and y and theta. So these are the parameters that I'd want to pass, and we also have m as the size, and let's say initially the cost would be 0 and the computed cost would increase. So or let's assign it directly. Let's compute the mean squares first, or the error. Now this would be the dot product of x and theta. This dot product of x and theta would represent our hypothesis, or the predicted value in other words. And we want to subtract it from y and square the difference. This is what is going to give us the mean squares. The next thing what we want to do is we want to sum all of these mean squares. So np.sum of mean squares. Once we sum the mean squares, we want to divide this by 2m. So divided by 2 times m. So what is this? This is our cost, and the function would return this cost. So let's return this expression. So this is our cost function. Now step 2. Step 2 is to define a function that would perform the gradient descent for a given parameters x, y, theta, and probably the learning rate, and as well we'd want to customize our number of iterations. So again, define a function saying perform gradient descent. So that can take in x, y, and theta, and learning rate alpha, as well as, let's say, number of iterations. And let's again say we want to make note of the size of the data set. We don't want to manipulate the actual data array directly, but let's take a copy of it. So we can nudge the parameters on the copy of the data. So I would say theta copy and theta dot copy. So this theta would be our numpy array, x and y as well will be our numpy arrays. And the next thing is we want to run several iterations. So for I in range, say for number of given iterations, we want to run an algorithm that we wrote again and again for these number of iterations until it converges at the global minimum. So let's calculate the mean error. So what would be our mean error? This would be our mean error. Dot product of x with theta subtracted with y. And we want to calculate the derivative term. So as we know that the derivative term will be the dot product of the mean error with the data set x. So mean error dot product with x. Now we've got the derivative term. The next thing what we want to do is we want to subtract the derivative term multiplied with the learning rate from theta. So theta copy will be theta copy minus learning rate times 1 over n times the derivative value. Now we've got this theta copy and we want to run this statement again and again until this theta is nudged to optimal value. So we want to calculate the cost in each iteration and make sure it is reducing. So let's calculate the cost as well. So we've already got a function that would compute the cost for us. Let's pass in x, y, and not theta, it is theta copy, because each time this is the numpy array that would get changed. And let's make note of this cost in each iteration so that we could visualize how the cost would decrease. Let's define cost history. Cost history as an array of values, and cost history dot append the cost in each of the iteration. Finally, after all the iterations, return I would want to return the optimized parameters and the cost function. Sorry, the cost history. Yes, this is what we want. Now this may not be the optimal code. If at all, we could also say if it reaches some threshold, which is if the error goes below so and so threshold, then stop the iterations and just return the values. It need not perform more iterations once it has already reached certain error threshold. So let's implement that as well. If cost goes below some error threshold, then just break. Okay. Now error threshold will be another parameter that we would want to pass, and let's define this. Done. Now let's define some initial values. Now let's initialize some values. We want to have a learning rate, that is alpha. Learning rate alpha. So let's set it to 0.01. Let's take smaller steps, and let's say I want 1,000 iterations, or let's say 1,400 iterations, 1400, and I want to initialize the parameters to some arbitrary values. Let's say for simplicity I would say 1 and 1. So theta initial is numpy array of 1 and 1. So theta 0 will be 1, theta 1 will be 1. Next step, let's find out what is the initial cost. So compute cost. Now before that, we wanted to stack ones to our data set because the coefficient of theta 0 is 1. So this is the most important step. np dot stack ones, np dot ones, how many ones, that is about our length of the data set, and the second column would be our data set, the training example itself, and we want to do it for columns. It's a column stack, so axis would be 1. Let's find out what is our x here. This is how the X matrix would look like. Fine. Let's find out what is the initial cost. So compute cost, and we want to pass x, y, and theta. So x, y, and initial theta value. So theta initial. So this is giving us 10. So it's a pretty less cost. We want to bring it closer to 0. So this would be our initial cost. Alright, Now let's run the gradient descent. So gradient descent, perform gradient descent, and we want to pass x, y, and theta initial, and the landing rate alpha, and number of iterations. So iterations, and let's say our threshold 0.003 something, and we want to capture the cost history and optimized parameters. Let's give optimized parameters and the cost history. And the next thing is we want to find out what is the optimized parameters. So it says the optimized parameter is minus 45.489 and minus 338. Let's try to plot the data. So plot data, we want to plot our data set. Okay, now on top of this, let's draw our linear model or a straight line that is parameterized by theta. So plot plt.plot, we want to pass the x values, and the y values will be given by the dot product of x with our optimized theta values. So what does this mean? This is mx plus c, or theta 0 plus theta 1 times x. So that is given by x with dot product of optimized parameters with it, which is nothing but our hypothesis. And we want to plot this as a straight line. Okay, looks like something has gone wrong. Let's find out whether the cost has decreased or increased. Let's plot the cost of our function. So plot plt.plot cost history. Okay, looks like it has increased. Probably we could take smaller steps and find out again. Okay. Or all right, let's say we would comment this for now. So let's try to run it again. Okay, now what about the cost? Seems like it's increasing. Let's go back and change the step size. Let's take far smaller steps and find out if there is an improvement. Okay, seems like there is some improvement. Let's orient this line a little bit different so it could converge faster. Let's say -2 and nudge a little more. Let's take a few more iterations and find out. Okay, now looks like we've fit the model here. So what is our optimized params? So optimized parameters. So these are the optimized parameters that we have. -2 and 1. It's quite closer. It's quite closer. Let's take even smaller steps. Okay, okay, right. Now that you see the cost has decreased over the number of iterations here. We have taken very, very small steps. So there is no steep descent of the cost. It's a very gradual decrease over the number of iterations. So that's when you try to code, try to nudge these values, increase the learning rate and decrease the number of iterations, and find out if you get the steepest, very steep cost history curve. So this curve will depend on the initialized parameters, the learning rate, as well as the arbitrarily set data values and the number of iterations. So this is a pretty much a very rough implementation of univariate linear regression with gradient descent. This is not a production ready code. This is only to show how to translate the math into Python code. Hope you enjoyed this session. Try it yourself and post it in the comments below. Do like and share if you found this video helpful. Thanks for listening.